Hello everyone, in this video we're going to be solving a nice differential equation. We have y prime equals 1 over x plus y plus 1 and we're going to be solving for y values. Before we start solving the problem, I just want to show you or share with you what Wolfram Alpha gave me when I input this into it. So here's the solution that I got from Wolfram Alpha. I'm like, wow, that's a little bit surprising. But anyways, go ahead and keep that in mind. And now we're going to proceed with the solution. Let's find out why this is the result. So we have y prime equals 1 over x plus y plus 1. And then we're going to go ahead and use substitution to solve this problem. A lot of times when you have the x and y mixed together but there's nothing else, we can kind of use this type of substitution. In this case, it will be very helpful, super helpful, to replace x plus y plus y plus 1 with something. How about z, right? So if you replace x plus y plus 1 with z, you're basically simplifying the right hand side a great deal. It just becomes 1 over z. Does that make sense? Okay, so that's going to be fairly simple, right? Now, let's see what this entails though, because we also have to evaluate y prime based on the substitution. X plus y plus 1 equals z. Now at this point, if you want, you can isolate y or just differentiate both sides. Doesn't matter, no big deal. If you differentiate both sides with respect to x, you're going to get 1 plus y prime plus 0, the derivative of a constant, equals the derivative of z with respect to x. Now the derivative of z with respect to x is also z prime, or you can write it as dz over dx, right? Which we're going to do a little later. And this is not partial differentiation because everything is a function of x. Make sense? Okay, cool. Now, we kind of got like a relationship between z prime and y prime. And that's what we need. So let's go ahead and isolate y prime, subtract 1. You get y prime equals z prime minus 1. So let's go ahead and substitute this into our equation, the original one. Okay? And that gives us the following. Z prime minus 1 equals 1 over z. Isn't that fairly simple? Look at that. Substitution is awesome. I love it. So where do we go from here? We're going to isolate z prime, write it as 1 over z plus 1, make a common denominator, z plus 1 over z. And now you want to replace z prime with dz over dx. You know why? Because this becomes a separable differential equation. And separable equations are just awesome, right? They're so easy to solve. All you have to do is separate and integrate. 2 steps. Easy, right? So let's go ahead and do this. Put the z terms on the left-hand side. So from here, we're going to do a little bit of cross multiplication. That gives us z over z plus 1 dz, right? Actually, yeah. We're going to divide both sides by that basically, or multiply by the reciprocal of this, right? dz, and that equals dx. Awesome. Now we can go ahead and integrate both sides. For a second, this just didn't look right to me. That's why I kind of stopped. So now we have an integral on the left-hand side. How do we integrate z over z plus 1? Easy. All you have to do is separate the numerator into pieces. So kind of like polynomial division, I should say, but you don't really need to do it. I can just do z plus 1 minus 1, which is equivalent to z divided by z plus 1. And then we can kind of separate these because this is going to become 1, right? Minus 1 over z plus 1. And the polynomial division is going to give you the same thing. You're going to get a quotient of 1 and a remainder of negative 1, which means this. So far, so good? Okay, so let's go ahead and integrate this expression. Obviously, this is a lot easier to integrate than z over z plus 1. Of course, you could also use substitution. You can call z plus 1 something, like let's say t or u or whatever, and then z would be u minus 1, so on and so forth. But I like this method better. Okay, so this is what we have. And on the right-hand side, we have the integral of dx, so that would be x plus c. Easy, right? We're going to put the constant on one side only because we don't really need constants on both sides. All right? Cool. Now, how do you integrate the expression on the left-hand side? Well, the integral of 1 with respect to z is just z, and the integral of 1 over z plus 1. Think about 1 over z dz, that would be ln, right? I mean, think about it. And I'm just going to avoid absolute value because I don't like it. But basically, you can use ln for this. But z plus 1 is not very much different. You're just adding 1. So we can write this as ln z plus 1. Of course, you have to make sure that z plus 1 is positive, so on and so forth, you know, in order for this to be well defined. But we don't have any, what is it called, bounds or boundaries, limits, upper and lower limits. This is an indefinite integral. So you can indefinitely do this. All right, great. So this is equal to x plus c. This is not the end goal though, right? Because we are trying to solve for what? Y. And you're like, why? Well, don't ask why, but you know, hopefully. So let's go ahead and back substitute. What is z? Z is, let's find out. I forgot. Z is x plus y plus 1. Okay, great. So let's go ahead and replace z with x plus y plus 1. And then again, inside the parentheses, I guess you could replace it with absolute value if you want, equals x plus c. Now, at this point, obviously, you can go ahead and put everything on the same side and set it equal to 0, or just bring the x over. Oh, by the way, I forgot. X cancels out. X minus x is equal to 0. So this cancels out and this cancels out. We kind of end up with something nicer, like y plus 1 minus ln x plus y plus 1 equals a constant. Awesome. You can definitely test it out and make sure that it satisfies the original equation. I'm not going to do it, but you can definitely do it. Let me just tell you what you're supposed to do. Just differentiate both sides with respect to x, and they're going to get some y prime, you know, some chain rule, whatever, ln stuff. And the derivative of the constant is going to be 0 on the right-hand side. So you're going to get an equation, isolate y prime from there, and hopefully you'll get 1 over x plus y plus 1. Check it out. It's a fun exercise. But I'm not going to do it here. Okay, you can do it. Now, let's get back to y Wolfram alpha threw at us that weird solution. So let's go ahead and work on this a little bit, and then I'll tell you, I'll show you that result one more time. Okay, cool. So this is what we got so far, and here's what we can do. And actually, this is probably going to be a little easier if I do it with the z. So allow me to go back to the z world and work from there. So we had z minus ln z plus 1, and I'll tell you why it's a little easier, because we have a single variable, right? I mean, we don't have a single variable, but I guess this is simpler, because imagine replacing z with x plus y plus 1, you're going to get a more complicated expression. So let's use the z version of the solution. And now here's what I'm going to do. A little bit of hocus pocus, okay? Ready? We're going to do e to the power both sides. And then that's going to be separated because we have a subtraction of exponents. So this can be written as e to the power z divided by e to the power ln z plus 1 equals e to the power x plus c. Awesome. That makes sense, right? If two things are equal, then e to the power those things are also equal. And now here's the critical part. E to the power ln something is something. So this is going to turn into z plus 1. Yay, this simplifies. And then this is going to become e to the power x plus c. What do you think I'm going to do next? Cross multiplication? Nope. We're going to actually cross multiply, but also divide by that. Anyways, let me do it first, and then I'll show you the next step. And now I'm going to go ahead and divide both sides by e to the z and e to the power x plus c. In other words, we get the following. Multiply both sides by e to the negative z first, and then divide by e to the x plus c, and you're going to get the following. Make sense? Hocus pocus, switch them around. Okay, cool. Now, here's what we get from here. What are we getting? Okay. Remember, the solution gave us Lambert's W function. Exactly, that's what we're going to use. But we do need the negative z here, so let's multiply both sides by negative 1 first, and then that's going to give us negative e to the power negative x minus c. By the way, you can kind of turn into k. K is negative c. They're both constants. And then we're just going to go ahead and divide both sides by e. That's going to give us negative z minus 1 times e to the power negative z minus 1. That's what I wanted to get. And here, dividing by e is just going to bring a minus 1. But guess what? That's another constant. So we can also write it as something like e to the power negative x plus c sub 1. I'm just using a different letter every time because the constants are changing, constantly changing, right? Okay, this is what we have so far, and now you can apply Lambert's W function on both sides, and yes, this is going to give you negative z minus 1 equals Lambert W function of negative e to the power negative x plus c sub 1, and then from here you can solve for z, and then you can solve for y. That, which brings us to the solution from Wolfram Alpha with the weird looking stuff. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.